Welcome to the OscopeWizard. I'm Gabe, the OscopeWizard. It is Baby Friday, aka Thursday, but seriously, Baby Friday. Let me get up and in focus so that you can see my blue eyes. They are blue. I think I actually have the color working correctly on my phone or on my camera. No, it's always working correctly on my phone. It's the camera that's giving me trouble. Got a light, sound, action. We are ready to start. Welcome. It is the soft end to another week. I basically am measuring my life now out in weeks, and on Tuesday's episode, we ended on a bit of a cliffhanger because we were trying to tune my amplifier. We got cameras plugged in. There we go. Cameras are plugged in. We are looking at the ceiling, but that's what we actually want to be looking at. So we're going to look at this guy today a little bit more closely to determine if we can measure the resistance of my cement resistor that was allegedly 8 ohms. But when we measured it, I measured 9.5 ohms, which was a little bit of a bummer, and also not 8 ohms. And I wanted to measure 9.5 ohms. A couple of people pointed some stuff out for me. So let me go back and let's talk about the things that they pointed out. One of the things they pointed out in some comments was that the markings on the resistor, 8R2 or 8RJ, which is actually what is on the resistor, means that it is a 5% tolerance resistor. So it's actually a pretty nice resistor that I purchased off of eBay. And then a second comment said, whoa, 9.5 ohms is way out of spec, but don't panic. You could use an HMC 8012 to make a much better measurement with a 4-wire technique. And I was using an HMC 8012 to make this measurement. In my defense, when we go to the website that I was using over here, see if I can get it into the frame. That's what we want to see. Over to the HMC 8012 website, and I hit manuals. This is the defense that I have, and I go to the user manual for the HMC 8012. It is not in English. That was one of the holdups that I had. I was trying to figure out from the pictures what I needed to hook up. So that was the main thing that was kind of throwing me off a little bit. The fact that it wasn't in English. So if I use these two inputs on my HMC here, let's get a better picture of it. I think I can get a better picture. I want this to be pretty close up so you can see what's happening. If I use these two inputs right here on the HMC, along with these two inputs, I can make a 4-wire resistance measurement. So let's get this in the screen, and we're going to measure this. We are going to measure this resistance. We're going to make it happen. Okay. I wish that my other camera was working, but it was making my sound choppy. So I have a couple extra wires here. And we're going to start out with the mistake that should have given me the clue that I needed. And we are well into the show, so let me start this timer. It's going to be a long one. It's going to be a little bit of a long one. I need to switch this over to resistance. There we go. It says open, which is good because these two wires are open. When I tie the wires together, what happens? 2 ohms. My HMC is measuring 2 ohms on some wires that are shorted together. That was my clue. There's always a clue to kind of help you to say, you're making a mistake. That was my clue. And I ignored my clue. Now, if I change this from a 2-wire measurement to a 4-wire measurement and still short it, what happens? Yeah, that was a good clue. When you measure a dead short and it says not 0, it says 2, that's a bad sign. So let's go over here and make 4-wire measurement. So what is the 4th wire doing? The 4th wire of this, I didn't even have it on resistance, and it was still measuring resistance. That's fun. I had it on continuity. That's cool. I'm going to change this from 2-wire to 4-wire. This 4th wire is going to act as a Kelvin connection, and in the link of the video that I am broadcasting right now, in the link to the video that I'm broadcasting, I have a link to the Bald Engineer's website, and he does a great job of explaining 4-wire measurements. And I encourage you to watch that link to get a little bit more detail. But now that I have 4 wires here, and I make a short, so I'm putting all these together. Oh, goodness. So now I have 4 wires all together. There we go, kind of a mess of wires together. But look what I'm measuring, 0.01 ohms. 0.01 ohms is pretty much 0. We're going to call that 0. Now, if I take the measurement on my resistor that I was measuring at 9.5 ohms, let's do the same thing. So I'm going to use my sense lines on my resistor to add a Kelvin connection. Again, check out the video from a real expert on multimeters. I am just using a multimeter, and I'm not an expert in multimeters, clearly. A lot of failures. If I plug that in, got it plugged in backwards because I'm measuring -8 ohms. Minus ohms is real tough to make. It's hard to get minus ohms going. There we go, 8 ohms. Let's look at that, 8 ohms, look at that. 8.08 ohms. That's a thumbs up. My resistors are nearly nigh on perfectly 8 ohms. And I am really sorry to the eBay seller who sold me 8 ohm resistors, perfect 8 ohm resistors, and then I trashed them. I didn't trash them too hard, but it wasn't great. It was not great. So let me switch over to the oscilloscope because I want to check out how to tune my amplifier. So I have the amplifier right here, and I want to tune it because we were overdriving the outputs last time, and I was using my resistors to do Bode'd plots of the outputs, and the Bode'd plots looked great. So if I hook all this up, get some cables out of the way, I want to make sure that I'm measuring the current and the voltage of my input. So I'm going to make a DC voltage measurement right here. And up here, I'm going to make an AC voltage measurement. I'm going to make a DC current measurement. I'm not going to make an AC voltage measurement. I'm going to make a DC current measurement. Come on, Gabe. Get with the program. Let's make all the connections into the front of the multimeter and plug the power in to the amplifier. Remember, I also have my oscilloscope connected via the function generator, and I am using my big differential probe, the ZHD16, plugged into the amplifier output. But here we go. Here we go. We're turned on. Let's just auto range up. Let's range up a little bit. Here we go. Range up. Range up. Oh, that's nope. There we go. I need to range up on my current. DCI. There we go. Range up. Okay, there we go. 24 volts. When nothing is going into the amplifier, you can measure 120 milliamps. So that is the steady state current of this amplifier. In the chat, I see. Yes. So in the chat, it was mentioned that the Kelvin connection is named after Lord Kelvin, who also has a unit of measurement that we never use unless you're an engineer. We always use Fahrenheit and Celsius, but there's another one that was named after Lord Kelvin, which describes a state of absolute zero, which is so cold that things cannot move. I wonder what absolute humidity is named. I guess that's rain, but we were at 90% humidity the other day, and that was so humid I could barely breathe, which was a little crazy. I'm gonna actually, when it's 90% humidity, it kind of feels like you're swimming through life. I'm gonna move this over a little bit and then turn on my oscilloscope. Can we see? I want to see, yeah, okay. It's not beautiful, but you can see the volts and the current, the voltage and the current over there in the corner. 90% humidity is called swimming. It does feel like you're swimming through life when it's 90% humidity. So now we are on to the oscilloscope. I am the OscopeWizard, so I'm at the instrument that I'm most comfortable with now. We're back in solid ground. But we begin by presetting, because I don't know what I was doing last, so I will preset the oscilloscope, get it to a known state. So I have channel 1 plugged into my input and channel 2 plugged into my output. Let's turn on channel 2. Let's get them both on the screen. Let's scale them a little bit so they fit good. There we go. And now, the other thing that I want to do is limit the bandwidth, because remember, I'm dealing with frequencies that go into my ear hole, so there is no reason to look at super high frequencies. I'm really more curious about super low frequencies, audio frequencies. And I'm going to use my waveform generator inside of the oscilloscope to generate a 100 hertz tone, so that is a sine wave, with 300 millivolts peak to peak of amplitude. So if I turn that on, if I turn that on and crank out my time per division here, oh, that's cranking in my time per division. There we go, cranking out my time per division. Let's get a couple of milliseconds on the screen. I almost panicked a little bit because I had the screen so zoomed in I couldn't see my sine wave, but there we are. Sine wave on the input. The output is overdriven, so it's off the screen. It's important to get it on the screen so I can make proper measurements. Let's see, how many divisions is it going to take? 5 volts per division. Let's make a couple of measurements. So we have an oscilloscope. Let's make some measurements. So I'm going to measure the amplitude and the RMS of my input, channel 1, and I also want to measure the voltage amplitude and RMS of my output. Okay, so I have an input and an output. Now, so now that I have all this set up, I want to go back and look at the data sheet really quickly. So where is my data sheet? Goodness gracious, there's my data sheet. That's what I want to look at. I want to go back to my amplifier data sheet and check out what the maximum input voltage is. The maximum input voltage could go up to 6 volts. I'm at 300 millivolts right now, and I have a lot of amplification turned on. So if I go back to my scope, I can see that I'm sending in 584 millivolts. I'm getting out 35 volts. That's quite an amplification. What if I send in 1 volt? So 1 volt peak to peak over here. What happens? Okay, my input is doing great. My output is chopped off. So I can see that I have overdriven the output of my amplifier. Also, notice my voltage dropped from 24 volts down to 18 volts, and I'm burning up 3.5 amps. So 18 volts times 3.5 amps. Let me turn down my, let's go the other way, down here. Back down to 300 millivolts. So you can see in the background, my output is still chopped off at the top. And I have to get all the way back down to 300, I think it's 300 millivolts before. Yeah, anything above 300 millivolts, and I start overdriving the output. So at 18 volts times 3.5 amps, how much power was being consumed? Let me just do a quick calculation. 18 times 3.5. If I go back over to my desktop, you can see 18 times 3.5 equals 63 watts. So 63 watts into 2 speakers is 30 watts per speaker. If I go back over to my data sheet, I can see that 8 ohm speakers can do 30 watts per speaker. So actually that was the 3118D2. But I believe it's remained the same for the TPA 3116D2. I could do 30 watts into 2 speakers. And that is basically what I'm doing. But the sound will be terrible because I'm chopping off the tops of the waveform, so that wouldn't sound perfect. And I want it to sound good. It's a big deal to sound good when you're listening to something. So on the, I'm kind of zoomed in on the, look, and when I get down to 300 millivolts, my power, my voltage is already dropped down to 20 volts, and I'm consuming 2.2 amps. So I'm getting major voltage drop when I actually or start amplifying anything. If I go down to 0 and just, if I go down to 0 by just disabling it, you can see my voltage kicks right back up to 24 volts, and the current drops down almost immediately to 120 milliamps. On my amplifier, I'm going to move my camera a little bit. On my amplifier are a couple of little variable resistors, potentiometers. I remembered the word! Potentiometers, and I can adjust these to adjust the gain of my output. So I can actually tune my inputs and outputs so that they match. Now, one of the things that I was curious about, because eventually I'm not going to use a signal generator. Eventually, I'm going to use my phone as my sound device. So I downloaded a little application on my phone that generates a tone. It'll play a tone. Let's see if we can hear it. Can you hear that little itty bitty tone? Maybe you can. It's like a low-pitched 100 hertz frequency. So I'm going to plug my phone into my circuit and measure the maximum output voltage from my phone, and that is going to tell me the maximum input voltage that will get into my amplifier, and that will also tell me how I need to tune the output so that they never distort, because if I turn the phone all the way up to maximum, I don't want to distort the outputs. Let's see. Plugging in my phone. You can see plugging in my phone. Now I'm going to plug it in to my input. And we'll see the signal pop up on the oscilloscope, which is why I have the oscilloscope playing. So now I'm at 75% volume. I can see, where did I go here? Did I lose my stream? I'm not sure if I lost my stream or not. I hope not. I can see that my input voltage is now at 75% volume, 225 millivolts. If I crank that up to maximum volume, so this is maximum volume, I am up to 1.12 volts. My output is at 31 volts, but chopped off the tops. So that's not great. So what I can do here is instead of using your ears to make some assumptions based on how things hear, what's the color of the sound, which I don't even know what the color of the sound means. Is it dark? Is it bright? That is a weird qualifier to a sound. I can look at an oscilloscope and figure out how to get my output to look like my input. So I can make an empirical measurement as opposed to a qualified measurement. What am I thinking about? Not a measurement, a feeling. So I'm going to adjust these attenuators to make my input and my output shape match. Another thing we'll notice, so as I adjust my attenuators, we'll also see the voltage and current change a little bit. So we're going to have a lot of moving parts all at the same time. Let's turn the attenuator and see what happens. So I turn it down. You'll notice that the voltage output remains the same. So basically that's telling me that the amplifier is pegged. And there we go. That is, see, now you can see where the voltage right here is clipped a little bit. Let's adjust it so it is not clipped, but it's as close to clipped as I can get it without clipping. So I think that is perfectly tuned. So we've actually tuned the amplifier's output. Qualitative versus quantitative. Thank you, chat. That is what I was looking for. This is a quantitative measurement based on empirical data versus a qualitative measurement, which would be based on the quality of the sound per my ear holes. And it's also calibrated. Man, these are all good points. Now I need to measure the other, because the amplifier has two outputs. I need to do this for both outputs. So I have my maximum input volume from my phone, which is a good representation of where we are going. And I want to make sure that I get my maximum output to my speakers without clipping. So I'm going to change the connection from my right speaker to my left speaker. But before I do that, I'm going to depower the circuit. I'm going to pull the energy out of the circuit. I don't have a power button right now. That is down the road. Down the road. Woo! I will say those resistors, they get hot, y'all. They actually are burning quite a bit of power, which is good. It's good. I want them to burn some power, but I don't want them to burn my fingers. Burning power, great. Burning fingers, less great. Less great. I got these huge these huge connectors that I'm trying to get on these leads, while the resistors are a little bit warm still. They're warmish. All right, I have that all plugged in. We can still see my voltage there. And now let's tune the other speaker, the other pretend speaker. Okay, so you can see it's overdriven just like its buddy was overdriven. I'm going to adjust the gain down. The voltage remains the same. Oh, whoa. The voltage remains the same. Goodness. Next time, I am not going to just leave my webcam hanging. I didn't mean to leave it hanging this time, but the camera was causing my voice to stutter. The camera on my phone. I was trying to use my camera on my... Oh my gosh. Scare me to death. Are you serious right now?
5 minutes remaining!
5 minutes remaining. So let's finish up tuning this other side, and we're going to make it even, we're going to make it match, and we're going to make it perfect. So we're almost tuned on this other side. You can see I'm just a little clipped right there. So let me adjust the potentiometer just a little bit, just a hair. And feel pretty good about it. I think that's pretty good, right? That's a little clipped. That is not clipped. Maybe a little. I don't think that's clipped. Maybe a little clip, like right at the top. Ah, we don't want that. We don't want it to be even a little clip, do we? Just, oh, there we go. Now we're not clipped. Now we are perfect. You'll notice before when we were overdriven, if I go back to my webcam, before when we were totally overdriven, my voltage had dropped down to 18 volts and my current was 3.5 amps. Now my voltage has only dropped to 21 volts and my current is 2 amps. And we are getting maximally undistorted power to my outputs. This would sound good. This would sound good, y'all. It would be awesome. And that's us manually tuning the speaker, which I think is pretty cool. Okay, next week, I think I've got the analog bit tuned. If there's any questions, throw them into the chat. Also, if you want to connect with me and ask me questions, please feel free. Comment on the video. You can find me on Twitter or Instagram at OscopeWizard. Yes, I'm as surprised as you are that at OscopeWizard was still available, but it was. So you can hit me up and I would be happy to chat with you. Next week, we're going to move over to the digital design portion of our project. So I have a Raspberry Pi. Of course, I have a Raspberry Pi. I mean, if you've seen the videos that I do on the channel, lots of Raspberry Pi stuff. I love Raspberry Pi. I have a Raspberry Pi Zero. The Raspberry Pi Zero does not have an audio output, though. So I also have a digital to analog converter chip right here. So it's going to take the digital audio from my Raspberry Pi, make it analog audio, and then that is going to be amplified and sent into my ear holes. Let's see, one of the questions was, will the resistor-based calibration hold for a speaker with variable frequency response? The speaker will have a slightly different response to the resistor, but I posit that the power distribution, the current will be the same, so I don't think the current and the voltage will change. The voltage will probably only shrink because now we'll have some capacitance and some inductance that will only shrink the voltage a little bit. It probably won't boost the voltage. Anyway, that's what I hope. We eventually will hook up the speakers and make a final measurement on everything once we get sound from my DAC going to it. I also am curious, what is the maximum voltage level coming out of my DAC, because that would force me to retune my potentiometers on my amp board. It's a whole system. This is system engineering. It's like all these movements. As soon as you add a new section to it, you got to start back over and tune everything from the bottom up, which is cool. I don't know all the nerds in the world, but I'd love to meet them. So please share this with a nerd in your life, and I will see you next time. I'm going to hang out in the chat. Thank you so much for joining the OscopeWizard, and happy Baby Friday. Bye.